How do you build a bridge where the wind is so violent it can twist steel like paper? In some regions of China, engineers aren't just defying gravity, they are confronting forces capable of destroying entire structures. Imagine a world where geography is no longer a constraint, but simply an adjustable variable. A world where mountains are moved to build megacities and where entire rivers are rerouted over thousands of kilometers to feed deserts of concrete. This is not the script of a science fiction film by Christopher Nolan. This is the physical reality of 21st century China. To understand the scale of what's happening, you have to look at the numbers. Over the past 30 years, China has consumed more cement than the United States did during the entire 20th century. But stopping at the numbers would be a mistake. What's truly fascinating is what I call invisible engineering. These are the hidden technologies, the one-of-a-kind machines and the bold physical solutions that allow China to build where everyone else has failed. Today, we are going to dissect the inner workings of the largest infrastructure projects in human history. Welcome to Blueprint Hub. Subscribe to the channel and get comfortable for what comes next. Part 1. Taming Water. The South-North Transfer, Odyssey. China faces a brutal natural imbalance. 80% of its water resources are in the south, but 50% of its population and most of its farmland are in the north. Northern China lives under permanent water stress. Beijing's answer? The South to North Water Diversion Project. Estimated cost, more than $60 billion. The challenge here is not simply digging a canal. It is about moving billions of cubic meters of water across mountain ranges and existing rivers. In Zhengzhou, engineers had to route water beneath the Yellow River through 2 giant tunnels, each 4 kilometers long. Why underneath? Because the Yellow River's bed is elevated by sediment. If the tunnel leaked, the pressure from the river above would crush everything. They had to invent tunnel boring shields capable of withstanding record hydrostatic pressures. It is a battle against gravity and sedimentation that now supplies water to more than 100 million people. Beyond the tunnels, the real feat lies in the massive pumping stations equipped with ultra-efficient axial flow pumps. These mechanical titans overcome hundreds of meters of elevation, maintaining a constant flow rate while preventing the massive surge pressures that could rupture the concrete conduits. It is a monumental victory of fluid dynamics over a hostile, uneven topography. Part 2. Bridges above the clouds, the physics of the abyss. In Guizhou province, the landscape looks like a crumpled sheet of paper. Canyons 500 meters deep, separate isolated plateaus. Building a bridge here is a logistical nightmare. Take the Beipanjiang Bridge, the highest in the world. At that height, 500 to 65 meters, the wind doesn't blow, it hits. Engineers had to use digital wind tunnels to design a deck that would not twist like the famous Tacoma Narrows Bridge. But the most impressive feat is the assembly. Instead of building from the ground up, they use prefabricated sections launched into the void by robotic cranes. Each suspension cable is a metallurgical achievement designed to withstand tensions of thousands of tons while remaining flexible against temperature changes that make the bridge grow or shrink by several centimeters every day. To counter these forces, engineers installed high-performance mass dampers and giant expansion joints. These systems allow the structure to breathe by absorbing the wind's kinetic energy in microseismic oscillations, preventing metal fatigue that would otherwise cause cracks under these invisible but constant stresses. Part 3. Rail on Permafrost. Tibet's Giant Freezer. The Qinghai-Tibet Railway is often called the railway to the sky. It reaches elevations of 5,000 meters. But the real challenge isn't oxygen, it's permafrost. The ground is permanently frozen, but with global warming and the heat released by passing trains, that ground can thaw. If it melts, it turns to mud and the rails sink. China's solution is a masterpiece of passive thermodynamics, thermosiphons. These are 5-meter metal tubes planted along the track. They contain liquid ammonia that evaporates at very low temperatures. In winter, heat from the ground causes the ammonia to evaporate, rise, cool upon contact with the air, and fall back down as liquid. This perpetual cycle extracts heat from the ground to keep it artificially frozen, even in summer. It is an invisible technology that turns unstable soil into a block of eternal ice beneath the train's wheels. To complement this, engineers added a layer of crushed rock along the embankment to act as a thermal shield. reflecting solar radiation. This dual-layered strategy, active cooling via ammonia and passive insulation, creates a stable, frozen foundation. It ensures the tracks remain perfectly aligned to the millimeter, even when the external environment swings by more than 30 degrees Celsius between seasons. Part 4. The Iron Monster, the industrialization of construction. One of the reasons China builds so fast is that it no longer sees a bridge or a tunnel as an architectural project, but as an industrial product. Enter the era of the SLJ 900/32, a 580-ton, 90-meter-long machine. Nicknamed the Iron Monster, this machine is an autonomous bridge launcher. It doesn't just transport a bridge segment, it carries it onto the previous pier, extends itself over the void to reach the next pier, and places the segment with millimeter precision. It eliminates the need for costly and dangerous scaffolding. Thanks to this machine, China can build a multi-kilometer viaduct in just weeks. It is this massive standardization, the creation of infinitely reproducible blueprints, that allows China to outperform all Western powers in terms of speed. What's fascinating is the balance management. The SLJ 900 uses a dynamic hydraulic counterweight system. As it extends into the void, the center of gravity is recalculated in milliseconds to prevent tipping. It is a ballet of laser sensors and high-pressure pistons that transforms a 580-ton mass into a surgical precision instrument. Part 5. The Energy of Titans, Beyond Three Gorges. The Three Gorges Dam is so colossal that it displays such a mass of water that Earth's moment of inertia changed, slowing its rotation by 0.06 microseconds. But today, China is going further with the Beipanjiang Dam. It is the first dam in the world to use 1 gigawatt generators. To prevent the concrete from cracking due to the intense heat generated during curing, engineers embedded thousands of sensors in a network of intelligent cooling pipes. AI monitors the concrete temperature in real time and adjusts the cold water flow. The achievement also lies in the chemical composition of the concrete. Engineers use low heat of hydration cement, a specific molecular formula that minimizes exothermic reactions. Combined with a closed-loop chilled water cooling system, this allows monolithic blocks to be poured without any microcracks, ensuring absolute water tightness under the reservoir's colossal pressure. It is a living dam that self-regulates. This mastery of hydroelectric power allows China to produce decarbonized energy on a scale that surpasses entire countries. Part 6. Exporting the Blueprint, the Geopolitics of Steel. This engineering power has become Beijing's most powerful diplomatic tool. Through the Belt and Road Initiative, China offers its services everywhere, from the port of Gwadar in Pakistan to the Mombasa-Nairobi Railway in Kenya. Engineering becomes an economic weapon. By building infrastructure where no one else wants to lend money, China secures strategic trade routes. But it is also a technical challenge, adapting Chinese standards to tropical or desert climates. Today, we are witnessing the emergence of a global infrastructure network made in China. However, this dominance raises a question. What happens when the maintenance of these projects depends entirely on a single nation? The blueprint then becomes a long-term dependency contract. This dependence is also technological. By imposing its own railway signaling standards or port management software, China creates a closed ecosystem. Once locked into these proprietary standards, a partner country finds itself unable to hire another provider for upgrades, making the Chinese blueprint virtually irreplaceable for generations. Part 7. The Intelligent Grid, Cities Built from Code. China's engineering isn't just about steel and concrete anymore. It's about the digital twin of civilization. In cities like Shenzhen and Hangzhou, the infrastructure is becoming sentient. Engineers are now building city brains, massive AI neural networks that monitor every bridge, every pipe, and every power line in real time. By embedding millions of 5G sensors into the very fabric of their constructions, they can predict a structural failure before it even happens. This is the ultimate evolution of invisible engineering, the transition from static objects to dynamic systems. They are using big data to optimize the flow of energy and water across the entire country, reducing waste on a scale that was mathematically impossible a decade ago. It is no longer just about building the biggest structure, it's about building the smartest one, where the blueprint is written in silicon as much as it is in stone. Part 8. The brutal reality of the future. China's invisible engineering forces us to reconsider our own limits. It proves that physical obstacles, whether void, ice, or distance, are merely calculation problems waiting for a solution. Whether through robotic bridge launchers or AI-managed cities, they have demonstrated that with enough capital and willpower, the impossible becomes routine. But gigantism comes at a price. The environmental impact of moving entire rivers is massive, and the financial debt tied to these pharaonic projects is beginning to weigh heavily on the global economy. China has built the future, but is it a sustainable future? Or are we witnessing the peak of an era that the Earth can no longer support? What is certain is that the science behind these machines and structures will remain one of the greatest achievements of our century. They have set a new benchmark for what humanity can achieve when we treat the planet itself as a canvas for our blueprints. If you want to keep exploring the technologies reshaping our civilization, you're in the right place. Subscribe to Blueprint Hub, turn on the bell, and tell me in the comments which project seems the most impossible to you. Is it the Iron Monster or the Digital City Brain? Stay curious. The future is being drawn one blueprint at a time. See you in the next video.